let's do some conditional probability problems. When drawing 5 cards from a standard deck of cards, find the probability of getting a face card if you have already been dealt the 6 of hearts. Okay, key. Have already been dealt. All right, so now, just want to take a quick pause. Some of you guys may not know what a face card is. Well, a face card in a deck of cards is like any card that has a picture of a person on it and they have a face. So that would be the jack, the queen, or the king. The rest of them are numbers or symbols, like an ace, for example. But the face cards are the jacks, the queens, and the kings. So let's start the problem. And if you want to give it a shot, pause the video, give it a shot. Okay, so the key here is we've already been dealt one of the cards. We've already been dealt the 6 of hearts. Now, I think the easiest way to do this is going to be kind of this way, saying the probability of getting a face given that I already got the 6 of hearts. So I think it'll be easiest to calculate this way as opposed to doing something like this. Because remember, we could use the formula, which says we have options. We could do the probability of getting a face given that 6 of hearts. This is equal to the probability of getting a face and the 6 of hearts divided by the probability of just getting the 6 of hearts. So you could do these 2 problems individually and answer this question, or you can just do this single problem and answer the question. And I think we have enough to be able to do it this way. So let's try it. Okay, so now, starting with just the standard deck of cards, what do we know? Just the denominator. Just we know that we've been dealt the 6 of hearts, but the rest of it's still there. There are 52 cards in a deck, but since we've already taken 1 out, there are now 51 cards, and out of those we need to choose 4 additional ones because we're pulling out a total of 5, but I already have the 6 of hearts in my hand. Now, for the numerator, take care of your condition first. First thing I'm going to do is guarantee getting a face card. Now, that means that I could either get 1 face card, I could get 2 face cards, I could get 3 face cards, I could get 4 face cards, because I already have 6 of hearts, so I could get 1, 2, or 3 of them. And this is because you have to remember there's the jack, the queen, the king, but they're of each suit. So I could get the jack, queen, king of hearts, jack, queen, king of diamonds, jack, queen, king of clubs, or jack, queen, king of spades, right? So there are a total of 12 different face cards. So it is possible for me to get 1 of them, 2 of them, 3 of them, 4 of them, or 4 of them, right? So, what seems the easiest? What seems the easiest? Well, I would need to do either the probability of me getting exactly 1 of them plus the probability of me getting 2 of them, right? So that would be this one. Probability of me getting 1 plus the probability of me getting 2 over 51 combinations 4, plus the probability of me getting 3 51 combinations 4. This seems like a lot of work. So instead, why don't we do it the other way? Why don't we do this? Why don't we do this? Why don't we do the complement? Why don't we do 1 minus the probability of me getting none of them? And then that'll be the same as the probability of me getting 1 or more face cards. Sounds like a easier way of doing it. So, what is the probability of me getting no face cards? Well, again, the denominator is still the same. So the numerator, take care of your condition first. Out of the 12 face cards, I'm going to get none of them. Now, you don't have to write that because 12 combination 0 is just the number 1, right? There's one way for me to do that. I don't get them. But what that does mean, though, is now how many cards are left in the deck? Well, there's 51 cards, and I can't get any of the face cards, so that's going to leave me with 39 cards to choose from. So out of the 39 remaining cards, I need to get 4 of those. And there you go. So thus will give us the probability of getting at least 1 face card, 1 being dealt from a deck of cards where I already know that I've been given 1 card. Fantastic. Okay, let's do another problem. When rolling a die twice and finding the product of the 2 rolls. Product, what does product mean? Multiplication. Okay, so when we multiply the 2 values together, what is the probability of getting a 9 if your first roll was a 3? Okay, so what's the probability of getting a 9 given that I already got a 3? All right, well, that seems not too bad. That seems not too bad. All right, so because when you think about it, we're rolling 2 dice, and this one already came up a 3. So that part of the game is done. This is finished. You can't change that. So now just how many total outcomes are left in this scenario? Well, there's a total of 6 possible outcomes. Whatever my die can roll. It can either roll a 1, a 2, a 3, a 4, a 5, or 6. So there's 6 possible outcomes. One decision, 6 choices, right? All right, numerator. Um, how many of those would result in me getting a 9, a product of 9? Well, 3 times 3 makes 9. So therefore, 1, 2, out of my 6 possible outcomes, that's the only one that will result in a 9. So there's a 1/6 chance of me getting a 9. Cool. All right. Not too bad. All right. So if that one made sense to you, try the next one. When rolling a die twice and finding the product of the 2 rolls, what is the probability of getting a 12 if you've already rolled a 1? All right, well, try the problem. I'll do it now. Okay. Now, this problem, I only put it in here because sometimes students get hung up on this one. Okay, so you'd say, all right, again, same situation. I've already rolled a 1, so that's already set in stone. That's done. There's one more dice roll to go, and it has 6 possible outcomes. And how many of those would result in me getting a product of 12? Well, because I've already rolled a 1 on my first die, right? We're going to say to ourselves, 1 times which of these numbers makes 12? Yeah, none of them. So therefore, it's 0. And so it's okay to put a 0. You say none of them work. So therefore, what's the probability? 0. I have no chance. I have already lost. That's it. Okay, so don't overthink those. Just go with them. Okay, now for this last one, this last set here of problems I want to go through in this video, I want to talk about the game roulette. If you've never seen the game roulette, let me bring up a little picture. Okay, so I have some images here for you. The idea of the game is you walk up to the table and there's all these different options. And the most simple way to bet is you pick any number and you put your chip on that number. So for example, you'd walk up and say, I'm going to put my chip on the number 9. Now, what that means is they're going to go to this wheel and they're going to drop a ball in the wheel and spin it around. And if that ball lands on the number 9, you win. If it lands anywhere else, you lose. So the key thing I want to point out here is how many spaces, how many different numbers are there on the roulette table? Well, if you kind of count, you can go all the way through. You'll see it goes up to 36. But also notice there are 2 numbers at the end. There's the numbers of 0 and 00 in America. Europe only has the single 0. But we're in America, so we're going to go with 00 too. So that means there are a total of 38 numbers to pick from. Okay? Now, if you want to learn how to play roulette, go to a casino or go somewhere else. But for us, that's all we're going to worry about. So we're going to do the idea of you're going to pick one number. If it comes up, you win. If it doesn't come up, you lose. So now, when playing the game of roulette, we're going to bet on one number at a time. What is the probability of losing 10 times in a row? So what is that saying? What's the probability of losing and losing and losing and losing and losing? So 1, 2, 3, 4, 5, dot, dot, dot. You get the idea. 10 times in a row. And the reason I give you this problem is I just want to have that conversation of, well, we know the rule would be the probability of losing times the probability of losing, given that you lost before, times the probability. So now the question is would this be true? Could you extrapolate this out? Could you take it out to 3 things? So this, then this, then this. And the answer is absolutely, right? And especially if you think about it, because these are independent probabilities. The likelihood of a number coming up twice or coming up once in a row, it doesn't matter. It's all independent. Just if first spin has no effect on the second spin. So essentially, just what we're saying is, what's the probability of me losing once times the probability of me losing again times the probability of me losing again. Da, 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 da. So that's really just going to be the probability of me losing raised to the 10th. So therefore, what is the likelihood of you losing in the game of roulette when you pick one number? So this would just be the probability of me losing. Well, we said there are 38 different numbers. And then how many of those would make me a loser? Well, 1 would make me a winner. So that means 37 of them would make me a loser. Which makes sense, right? I have a very high likelihood of losing because that is me. I am a loser. No, I'm just kidding. But are going to lose. That's the whole point of gambling, right? So now, what would this be? 37 divided by 38, which is 97.36% of the time, but then I'm going to raise that to the 10th. So that means the likelihood of me playing 10 times in a row and losing 10 times in a row is 76.5916-ish%. So that means when you bet 10 times in a row, 3/4 of the time you're going to lose. Okay. What about 20 times in a row? What about 30 times in a row? Well, I mean, I'm hoping I don't need to do this again. So you've probably already figured out this would be the probability of you losing. 20 times, right? So therefore, this would be 37 raised to the 38th. So what is the likelihood that if you come in and play 20 times, you're going to lose all 20 times? Should that probability be higher than 76% or lower than 76%? Well, just think about it in reality. The logic says, all right, you play once, 37 out of 38 times you're going to lose. That's pretty high. But the more you play, you're going to have a better chance of winning, right? That you're more likely to win because you're playing more, so you're losing more money, right? So, all right, so let's see. So 37 out of 38 raised to the 20th would result in 0.5866. So just over half, 58.66% of the time, you are going to lose 20 spins in a row. What about 30 spins in a row? What would that be? 37 out of 38 raised to the 30th. Actually, you know what? And I'm going to be a little strategic about this. I'm going to do it 35 times. 35 times. There we go. What does that come out to be? What does that come out to be? This is going to be amazing. 37 over 38 raised to the 35th. And that is 0.3932. So about 40% of the time, you are going to lose 35 spins in a row. Wow. Now, what does that mean? Well, the real reason I go there is when you play in Las Vegas, I believe the payout is $36, maybe $35, somewhere in that range. I don't bet. I'm not a gambler, but it's something in that range. So the point being, if you spin 35 times in a row and then you win on your 36th time, you didn't win anything. You just got your money back. And so that's the whole point is and we're going to actually calculate later on in another section something called expected value. And we're going to figure out how much do you actually expect to win or lose. Right now, we just need to get the probabilities. And so right now, you can kind of play this game and say, wow, if I go and bet 35 times in a row, 40% of the time, I'm going to lose all 35 spins. Not very much fun, but what Vegas is counting on is that one time where you do win, and that is a lot of fun. So nonetheless, I hope this was helpful. I hope this helps you understand conditional probability. I'll see you in the next video.